Okay.
Are you recording as well?
I'm going to start recording too, but mine always dies, but I'm going to start it for fun. So you are recording now? Okay. All right.
Do you want an extra backup computer recording it besides this one?
No, that's fine. Oh, so, yeah. Okay. Can you hear me?
Keep saying something.
Yeah. Can you hear me now? Okay. So I can hear you on as the feedback. So make sure you unplug that.
Okay, yeah.
Did you resumed? Okay. All right. We're all set for the first few minutes. Okay. I think you'll be okay, but that's fine. My speaker's muted. Okay. Yeah, how's it going? Okay. All right. Awesome. All right. So today we're on this section, GPS. We're continuing to talk about getting data into a GIS system. So last week we talked mostly about digitizing. This week we're going to talk about the global positioning system. And then finally, well, actually, no, there's 2 more weeks. The next, I already have the week after posted up here. It's on remote sensing and imagery and georectification. That's taking an image and putting it into geographic space. So that's what we'll talk about next week. You might have heard me talk to the TA here for a second, Elida. That is one of the labs that people have the most difficulty with. Kind of sometimes people get frustrated with it. So if you want to get a jump start on it, you can, but make sure that it's one of those labs where you have to actually like follow it, unless you really understand what's going on. I guess then you could get into it, but it is important that you do the steps in the right order until you figure out what's happening, because if you don't, then it's hard to explain until we teach the concept. But basically, you're moving an image around a geographic space, and if you're telling it to move the wrong image, you might be telling it to move the image that's already in the correct geographic space that you're trying to match the other one. And so if you keep moving one and that's not supposed to be moved, it's kind of like you're creating a moving target, and usually you have to start all over at that point. So anyway, that's up there for you to start on. Today's lab is actually not going to be done primarily on the computers. There is a computer part to do, but we have to do the other part first. And so after we do the lecture today, you're free to go out and do this lab 5, which we'll go over at the very end of the lecture. Okay, but you probably won't be here much past 3 today, because we'll do the lecture and then say go ahead and go out and do that. And then this is just the starting of the lab. And the second computer part, there's a couple questions to answer once you do the computer part. But even that part should only take you about a half hour at the most to do. It's not that complicated. Okay, so we've got probably one of the least complicated labs and maybe one that'll cause a few headaches next week, back to back here. All right. So let's start talking about GPS. And when I first started lecturing about GPS, not everybody knew what it was, but I think almost everybody has at least some understanding of what GPS is. However, we're going to learn in greater detail what it entails, what it means, and how it works. And that will give you a greater idea of how it can be used, where it's not appropriate to use it, and what causes error in the GPS system. So GPS does stand for Global Positioning System. All right, so the Global Positioning System is based on this older concept of navigating through celestial objects. And the celestial objects that the Global Positioning System uses are satellites that we as a society have put up there that are orbiting the Earth. But we're still calculating our position based on the position of these satellites that are out there. So navigating using celestial objects goes back really far. Navigating at sea depended on this sort of navigation. And using instruments like this to triangulate, figure out an angle to an object, and use it to calculate a location. Here's a sextant, which was an object used to calculate the angle above a horizon to measure their position of a boat. All right. So there's another acronym that you've seen me use already a few times. It's called GNSS, and this acronym stands for Global Navigation Satellite System. It's just commonly used as a general term for any satellite system that can be used to calculate your position. And there are more than one system. So the GPS system, which was originally known as Navstar, created by the United States government back in the early 1980s, is what commonly we call the GPS, the Global Positioning System. However, the European Union actually started the effort a while ago, but they plan to get their system operational by 2019. It's called Galileo, satellite system. The Russian government has had a system of satellites since 2012. They started it way back in the 90s, but it's been operational since 2012, called GLONASS. And it's an abbreviation or an acronym in Russian. I don't understand what that is. Obviously, that's not Cyrillic alphabet, but there are a few other satellite systems under development. Okay, there's one in China and one in India. India already has a system of satellites up there for collecting natural resource information, like what we'll learn about next week. So they have satellites that have multispectral scanners on them, just like the United States and Japan and other what we think of as industrial nations. So they have a history of having satellites. So this will be a system that does positioning, which is a little bit different, but still involves the satellites in orbit.
Quick question: do you know if the U.S. ever rents out some of its data to other nations like Japan instead of put up another set of?
You mean global positioning data?
Yeah.
Or global positioning system? So the GPS system can be used by anybody, and there are multiple commercial, non-government entities that that connect to the system and utilize it for all sorts of civilian purposes. So it's no longer a strictly military system. In fact, during the Clinton era, when President Clinton was president, the system was opened up for even the high accuracy measements could be utilized. Now, I'm not sure. I don't have like a super secret clearance or anything, so maybe there's even a better system out there. But the system that is in place is capable of getting very high accuracy measurements. So I don't think it's likely.
Okay.
We can already pull down, figure out a coordinate to one or 2 centimeters in real time. Now that does take a little bit of, not just your off-the-shelf smartphone that does that, but it does have that capability. Now, one reason that we talk about these is that even the GLONASS system is accessible by commercial vendors, have the ability to connect into this system. So there are a number of devices that, and the reason why we use this term GNSS, there are a number of devices that can connect to these other satellite systems, and that provides a even more precise location. Typically nowadays it's just GPS and GLONASS, but all of these systems together. It always thinks that it's going to. All right. It always thinks that together. I'm sorry. All of these things together are under the umbrella of the Global Navigation Satellite System. All right. So right now that's primarily GLONASS and GPS, but there are actually other technologies that have been used, and we'll talk about some of these, to improve the accuracy of GPS or GLONASS. We'll talk about the Wide Area Augmentation System, WASS, and a few other things here. So, I've already said that this involves the satellites circling the Earth, but these satellites are transmitting a signal, okay? And anybody with a receiver that's capable of interpreting the signal that the satellites are sending out, and also it needs to do some processing, can figure out their position. We'll talk about the processing that goes on inside the systems here. All right. Now, these are quite far, remarkably. They're pretty far away from the Earth. Okay, this is the distance from the Earth here. Somewhere in the range, the GPS and the GLONASS and the GNS, somewhere in the range of 15,000 miles away from the center of the Earth there. So you can see in relationship to things like the Hubble telescope or the International Space Station, these are really, really, really far away from the Earth. And they're moving quickly through the horizon. It's kind of neat that we can pull our position down to a centimeter based on just the proximity and the orbit of these satellites when they're so far away. So they're constantly sending out a signal. The satellites themselves, they don't receive any signals. So some people, they're like, when GPS was first invented, people would be like, I'm not going to use a GPS because it's going to record my position somehow. Well, especially when GPS was first invented, that's not possible. You're not sending anything back to the satellite itself. Anybody with just a GPS signal is only a passive participant in this positioning process. I use a lot of P's there, but nowadays, of course, we have cell phones, and if you have data, there are apps that could broadcast your location. That's a different security concern. The GPS system itself is not broadcasting or recording or doesn't even know anything about you. It's just broadcast. Each of these satellites is just broadcasting its location for you to benefit from. So there are a number of segments that we're going to talk about, and each of these segments is important for calculating a position. We've got the satellite segment. The satellite segment is one we've pretty much already talked about, the satellites that are orbiting the Earth. The user segment, those instruments that people use to receive the signals from the satellites. And finally, the control segment. So, these are pieces of electronics that wear out over time. And, we do every once in a while launch a new GPS satellite. Saying I mean the government of the United States launches a satellite to go into orbit to accompany these satellites that wear out over time. And then also the control segment monitors and make sure that these satellites are staying in the orbits that they are intended to be on. So here's a picture of one of the GPS satellites. Not extremely large. They're smaller than a car, but they're still pretty small objects. All right, there are in a full constellation approximately 30 satellites. Now there doesn't have to be 30 satellites. There can be as few as about 27 in order for them to do their job. And there can actually be a few more, but there's the ideal situation is 30, so that there is some redundancy to the system itself. So there are 6 orbital planes. In other words, there are only 6 different orbits. There are multiple satellites on the same orbit. There's a 12-hour return interval for each satellite. So remember, we said they're out 15,000 miles away from Earth, and they're traveling. They'll be the same point overhead. Well, not the same point overhead because the Earth's also spinning, but they'll be the same point in their orbit every 12 hours. So they're going really, really quickly. What this means, and this is important, so the reason for all of this is so that any given time you'll have at least 4 and hopefully a little more than 8 satellites above the horizon for any spot on Earth at any particular time. You need at least 4 to calculate your position. We'll talk about why. When I say calculate, you need at least 4 for the GPS device to calculate its position. And it's the more you have, the tighter the tighter your position will be. The more precise, the more known your exact position will be. And so over time, there have been different amounts of satellites in orbit. We've launched different satellites at different times. This isn't like any material on the test. This is just for your information. All right, the stations in the GPS control segment, this is the only slide on the control segment, but you'll notice that we have control stations for these satellites spaced all over the Earth. And so at any particular time, all of the satellites can be contacted and monitored, so they never go out of range, because there's one in Hawaii, Colorado Springs, the middle of the Atlantic Ocean, the middle of the Indian Ocean, and on the edge, the eastern edge. Well, I guess we would call that the eastern edge of the Pacific.
I assume all those places are on islands.
The western edge of the Pacific. Yes. These 4 are islands. Colorado Springs is not an island. Right. And like, for example, Diego Garcia is a long time military base for the British, but we have our GPS control segment on that location. All right, the GLONASS, which is the Russian version, they actually have 46 ground stations on Russian territory. Their territory covers a very wide portion of the Earth, and then they have 8 in neighboring countries. They have an even larger sphere of influence there. 3 in Antarctica and 1 in Brazil. So they also have extensive control network. So all the satellites can be tracked in real time during their entire orbit, whether or not it's the GPS or GNS system. You can actually go on, there are multiple places. This is one at NASA where you can track the location of the satellites. All right, the user state segment is what we normally interact with. Okay, these are devices. This is a device that we actually still use. We own 4 of these, and we use this Trimble GHY 6000 to collect GPS measurements. And the Trimble GHY has like a smartphone built in. It actually runs kind of the old Windows. Maybe you remember that, maybe you don't. They called it Windows CE for a little while, then they changed it to Windows Mobile. That got confusing because now there's a new Windows Phone thing that I don't think anybody actually uses. But
I use that phone.
oh, you have a Windows Phone? All right. Well, this is the older one. Did you use one of these?
No.
Okay. So I actually had one of these kinds of phones. It's built in, and the software that runs on it though could run on a different GPS platform, but it wouldn't have the additional capabilities that we'll talk about later. More often, so this instrument costs thousands of dollars because it has the ability to get a very accurate measurement, has a smartphone built in, things like that. This object here, or this GPS here, is one that you could buy at Walmart or Best Buy or something, and much more common. You may own one of these Garmin eTrex or other consumer grade GPS measurement device. Now, these often have some abilities built in that you may or may not have in a smartphone app, but the GPS that's in these devices isn't actually operationally that much more capable than the GPS in most smartphones. So more and more we're seeing these devices replaced when this has the advantage that it's kind of ruggedized, but if you didn't have that, more and more we're seeing people just use smartphone apps to fill this niche of a consumer grade GPS. Okay. So these are used to get 3D points. So we already said that the satellites, they come back to the same place in their orbit every 12 hours, which implies that they circle the Earth twice daily. So you should have 4, and I mean I've seen even more than 12, but you should have actually more than 8, up to 12 sometimes, satellites visible from any unobstructed location at a time. So we haven't stated this so far, but GPS actually won't work unless you have a direct line to the satellite. So if you're standing and there's a big, huge mountain and the satellite is on the horizon, your direct shot back to the satellite, you won't receive a signal. Same if I were to go out and stand right next to the building and I can only see part of the sky. I'm not seeing as many satellites. All right. Inside a building, you're not going to get a reliable GPS signal. You might get one, but we'll talk about why that's a problem. Okay, the location that you get won't be that accurate. So each satellite continuously broadcasts a signal on 2 carrier frequencies. We call it L1 and L2. They also transmit coded signals, which are modulations of their carriers signals. They have different frequencies. Again, don't worry. This isn't on this table of frequencies or anything. Isn't on the test. It's for informational purposes. Although you might be tested on the differences between the two different types of frequencies, which we'll talk about here in a second. So one of the signals that's sent over, those contain the modulated signals. Those are the signals that are used to calculate your position. And then two other pieces of information that are called the almanac and the ephemeris. Now, those pieces of information are things like the position of the satellites and all of the other satellites, so that they basically aid the user device in getting a fix on the other satellites quickly, because it knows where to look for them, and it helps them calculate it. Helps the device calculate the position faster. So the two signals are the two modulated signals are the course acquisition code and the P code. So the CA code and the P code. Okay, and you can see the difference in the frequency. Okay, this one's a higher frequency than this. So the P code, the precision code, has a higher frequency. In other words, it's sending signals, and the difference between, like, let's just say it was sending a bunch of on and offs, zeros and ones, zeros and ones, zeros and ones. It can send them with more precision than this one. Okay, sending with less precision, ons and offs, yeses or nos. And you'll see that is going to be the difference in how precise it is. Okay. So, yeah, I already said the almanac is used to determine the location of every satellite and the GPS location. The almanac and the ephemeris data is used for broadcasting satellite health, clock corrections, etc. So, one of the things is that the clocks in the satellite are precise atomic clocks. Okay? The clocks in most devices, they're not as precise, and so it allows the GPS receiver to accurately calculate the position of the broadcasting satellite. Yeah. The receiver has an internal clock, and actually all GPS, this is what makes the GPS system work, this is one of the things. This is one of the key elements, though. All the GPS receivers have a clock in them, and that clock is used to generate a signal, like a bunch of ons and offs, ones and zeros. 1 1 1 1 0 1 1 1 1. Just think about it like that. Okay, a bunch of ons and offs, and it's being generated based on the clock. So the knowledge of what that signal is generating is vital, because the satellites themselves, with their extremely accurate atomic clocks, are creating the exact same code based on time. So in other words, they're generating and sending out 111 000 111 000 just a bunch of numbers, and they're sending out that signal. And so when you are using a GPS device, you're using the difference in those two signals to calculate a range measurement. Okay? So you're figuring out, or your GPS device is figuring out how far away you are from each of these satellites. And your position is going to be based on your position is going to be based on these range measurements from multiple satellites. Okay? So it can if it knows how far away it is, if it knows the difference in the travel time of the signal and the speed of light, it can figure out how far away it is from all the other satellites. So how does it figure out this travel time? Okay? Well, it figures out the travel time because it knows when it generated the signal, and it compares the signal that it received from the satellite and looks at the offset. And that's the travel time, how long it took. So it says this signal was created at 7:20 p.m. and I got it at 7:21 p.m. So it took a second. Well, knowing that the speed of light is this number, okay, I can figure out how far away the satellite is at that second, at that time period. Speed of light is very, very fast. Okay? Sometimes we say 3 times 10 to the negative 1 meters per second. Okay? For every kilometer, count 3 seconds. For every mile, count that's thunder. Okay, but the speed of light is very, very fast, so it allows for very precise measurement. So these two different types of signals, the coded or the CA measurements, have different advantages and disadvantages. So most handheld commercial satellites, commercial user devices like your smartphone, they use this signal. It's rapid. You only need a few seconds per satellite. It's robust. It's inexpensive. You can get a GPS sensor now for, well, the actual like chip that goes into the smartphone retails for $20. Okay, so it's adding a very small portion to your smartphone. You might get it built into a Garmin for less than $100. It's inexpensive, but it's relatively porous, somewhere between 0.5 meter and 10 meters. The carrier phase signals, they require a little longer time periods to lock, get all the satellites. Because the signal is so precise, you need an uninterrupted signal. It does require a more expensive receiver, but they provide high accuracies. Usually we would say a few centimeters, but it's not unreasonable to get down to a millimeter. So this is what I was talking about. So you can imagine these as little ons and offs, or ones and zeros. So this is off, on for a little while, off for a little while, on for a little while, right? It creates a pattern. This is the pattern that the satellite is broadcasting. This is the pattern that the receiver is generating from its own clock. And so what the receiver does is match the signal from the signal that it received to the signal that it generated. And this distance here, in terms of how far off these two are, is the travel time, how long it took to get there. And so using the speed of light, it can calculate its distance to that satellite. Now it has to do that for multiple satellites. Okay? So if I only calculate my distance to one satellite, I could be anywhere on this sphere. That wouldn't be very helpful. Now it's possible that this only intersects the Earth in a few places, but still it's not precise enough. If I know my distance to two satellites, then I could be anywhere on the place where the two satellites intersect. So it's basically a circle. I could be anywhere on that circle. And again, it's not precise enough because it could be in a lot of places on the Earth. Okay. If I know my distance to three satellites, I could be anywhere on the interface of all three of those spheres, which is, if the point is measured exactly, the interface of all three of those spheres will be a single point. However, since there's error involved, it's not a single point. It's usually a box in space. It can be anywhere within that box. So that fourth satellite is needed in order to really pin down that location. With four satellites, the receiver at one point where the four satellites intersect. So before your GPS will report a location to you, it needs four satellites. The GPS calculates a range, but there's uncertainty to the calculation. I mean, if you think about what's going on, traveling around the Earth really, really fast, and there are errors in range measurements. These errors in range measurements are what account for the uncertainty in the GPS position. Okay, where are we? We're at this position, but there's error associated with it. So think about calculating our position to various satellites. Here we got 3 satellites shown. We could be anywhere within that box because there's range uncertainty associated with each of these distances. The distance to this receiver, the distance to this receiver, and the distance to this receiver. So we could be anywhere in this range uncertainty band where all those intersect. So anywhere within this, in this case, we see it as a box. I don't mean that it has square sides, but that's our range of uncertainty. Okay, so we've got lots of sources of error, and some of these sources of error can actually be modeled. Okay, so and accounted for. So the satellite clock error typically gives us about 1 meter, satellite position error about 1 meter, receiver error about 1.5 meters, atmospheric ionic effects about 4 meters. So just things that are associated with the GPS system itself are giving us about 7.5 meters of accuracy. Of range error. There are other things, like this is a very big problem, multipath, okay? So that's some additional error depending on the conditions received of the receiver quality. Multipath is when the satellite signal doesn't travel directly to us. It bounces off of some other object. So this is what I meant by being indoors. If we're indoors and we're receiving a GPS location, it's because that signal bounced off several other objects before it got to us, because it can't penetrate the building that we're in. And what this means is that range measurement is off, okay? So GPS position indoors is never really of good quality. It can add 10, 50, even 100 meters of error onto a point. Also, in like urban canyons, inside of a area that's got buildings on board, or a real canyon, we can get multipath errors that can take our position off. All right. There are systems that kind of account for some of these problems. Like if you noticed, you've driven in a city like Chicago, this is Chicago, or New York, and you use your phone as a GPS device, it keeps you on pretty well. Well, that's because there's some processing going on that's saying, okay, well, all of a sudden I can't be like way over there and then back over here. So the GPS, it's not the GPS system, but it's the device that you're using is accounting for the fact that there could be some multipath error and correcting that. Another thing that can cause your uncertainty, the positional uncertainty, besides multipath, is the satellites being too low on the horizon. If the satellites are too low on the horizon, they get blocked by buildings. It can either create more multipath or just make it so that you can't even, your device can't see those satellites. And this creates another problem. This creates the problem of if all the satellites are clustered around each other in the same place, even if you can get 4 or 5 of them, if they're all in the same location relative to you, or very similar location relative to you, your area of uncertainty actually gets larger. See how the area of uncertainty from 3 satellites that are directly above you is very large, whereas the area of uncertainty from 3 satellites that are spaced evenly on the horizon is really small. And this is referred to as PDOT, okay, or it stands for a position dilution of precision. Okay? So another thing that buildings can create is this problem. So not only multipath, but they can create basically high PDOT values because you can't see the satellites that are over here. That would allow your position to be reported more precisely. So it's a measure of satellite spacing. So your device can actually calculate this because it knows the position of the satellites they broadcast. So it can calculate the satellite, your PDOF based on the spacing. So typically they range from 2 to 10, but they can be as low as 1. They can be up in the hundreds if the satellites that you're getting are all right next to each other. So the lower PDOFs are better. You know, a couple of years ago, I started, like 3 or 4 years ago, I started building little unmanned aerial vehicles for fun. You know, it's turned into research, but I don't build them anymore. I just use them. But when we built them, it was interesting because they use a GPS to acquire their position. And so sometimes I noticed, and other people do this, if you fly too close to a building, what happens sometimes is that it seems like the drone, the UAV, will just drift into the building. Bam. Okay, why is it doing that? Well, there are a few reasons why it's doing that. One is that the position all of a sudden changed because of a multipath error. So it bounced off of the building or bounced off a different object. And so the multipath error made that position be in a totally different location. Okay. Another reason is because of this PDOF error. And most UAVs actually contain, most drones contain fail-safes. They won't even let you take off if the PDOF is too high because it knows that that location could be off by a lot. You could crash into a building or something. They're getting more and more capabilities. Even the consumer models have the capabilities now to to see, not really see, but just they have sensors. They can detect buildings. They can detect movement. But really, if you only have a GPS location to go with, and that GPS location is bad, that's why these kinds of things happen. Some people call it flyaway. It all of a sudden started flying away. Well, it wasn't that it was flying away. It actually thought that its position was changing, and it needed to go it needed to stay where it was. All right. So range errors in the dilution of precision combine to affect GPS position accuracies. So current consumer-grade CA code receivers typically provide accuracies between 3 meters and 30 meters for a single fix. So that's what we're going to get when we go out. Okay, we're actually going to test that. We're going to go out with our smartphones and test what kind of accuracy we're going to get. All right, the average accuracy and also what the average points will be. So improvements can be possible with multiple fixes averaged. So that's really what we're going to do. So we're all going to go out and collect the same location today or sometime before next week. And we're going to basically simulate having multiple fixes. So everybody's smartphone is going to report a different location. And guess what? Because these errors are kind of what we would call normally distributed about the true location, when we average the locations of multiple fixes, almost always we get a better location from the average of multiple fixes. Okay? So this is true actually with CA code receivers like we're going to use, or carrier phase receivers like the GHY. They can be a few centimeters or millimeters away. So there are differences in accuracies due to technology applied. We're gonna talk a little bit about things that we can do to make the accuracy go up even more. Okay, so here's an example. This is from the book, and it says a PDA base. What does PDA mean?
maybe talking about a home device. Just
Yeah, that's what they called smartphones grandpas, basically. Like the things that became smartphones were called PDAs, stands for personal digital assistant. Okay, like a BlackBerry, or even before BlackBerries, they had things that were kind of, they had the screen. You had to use a stylus all the time. Anyway, or not even, they didn't even have a touch screen. You got a Palm Pilot, one example. So this is a PDA GPS. Okay. Yeah. And then it's running ArcPad, which is an old system. I don't know if this is actually still in the book or not. I didn't look through the chapter, but it shows that the average error is right around 5 meters. Okay. But it can be as much as 20 meters. So the mean error is a little over 5 meters, 6.7 meters. Okay. Okay. Here's another one. Using this is basically showing the error out of the open. This is showing the error in a canopy. A canopy meaning tree canopy. The errors get higher. Up to 13 meters is the average error. Okay. All right. If we were to look at different types of devices, so here's a Garmin with a wide area augmentation system receiver in it. That you're going to get down to about 2 meters. We'll talk about what WAS here is in a second. Here's a Trimble GO3, which is a nice system. This is just the raw data, 3 meters. If it's post-process, we'll talk about what that means. You get better accuracy. A Trimble GOXT, like the one I said cost thousands of dollars that we use, well, that was a GOXH. GOXT is an earlier version. It could get down close to a half a meter post-process. Different time, different accuracies. So different receivers are capable of getting a better value. But below forest canopy, where there's lots of multi-path and satellites that you have to get thrown out because the receiver can't see them, see the accuracies, they all get higher. It's harder to tell, but the scale here changes. It's 8 is the maximum here. 4 is the maximum on that one. So the errors got larger, relatively speaking.
So in theory, if you were doing research out in the forest, would it be smart to have a GPS on a stick that you can stick up above the canopy, or?
That would work if you had one that was that tall. That would probably be pretty hard. For my dissertation work, we had this issue, and so what we did was we calculated a position outside of the canopy, and then used something that I brought up, a total station-like device, to measure the angle and the distance into different positions. So I went out and held up a rod with a prism in it, and they shot that prism so that position was also very accurate. So that's another way to do it. Another way to do it is to go out there with your device and take 100 points, so you can average them all together. That'll bring your accuracies up a little bit. But this actually was already the average of 300 fixes. So you can see even with 300 fixes, there were some differences between forest and open areas in terms of the accuracy. All right, another thing that you can do to improve your accuracy is actually use 2 units. Refer to this as differential GPS. And the differential GPS is using 2 GPS systems in order to use one to calculate the amount of error in the other. This involves setting up a station that is continuously recording GPS values at a known location. In other words, that location's coordinates are known to the millimeter, and you set a GPS up on top of that to record a location. In the United States now, we actually have a network of continuously operating receivers, GPS receivers. We call it the CORS system, continuously operating receiver system. And the CORS system continuously records it so that you don't actually have to have your own base station, because you can connect after the fact to one of these receivers. So it relies on this concept that the error in the GPS is spatially related, or spatially autocorrelated is what it's often referred to. What that means is that the error my GPS receives here is going to be almost identical to if I move over here at the exact, if I had two of the identical receivers at the exact same time, and I was only a meter apart, the error would be almost exactly the same. If I move a mile away, it's still going to be pretty close. 10 miles away, it's going to be a little bit different, but it's still going to be similar. 20 miles away, and so on. Okay? So these continuously operating base stations are spaced so that you're always about 50 to 70 miles away from a base station at any time. So if you want to get even more precise, you could set up your own you could set up your own base station and have it calculate a location. So that's how differential GPS works. You have to have two GPS devices collecting simultaneously, and the base station, you also have to know the real point to some level of significance that you care about. You have to know its real location. Differential positioning. Okay? So at the base station, we have the measured position that the GPS satellite gets, and we have the known position. We can calculate the error as a direction and a distance. So we just go the opposite direction at what we call the rover. The rover is the device that's in the field where we don't know its real location. And so we use the corrective factor we got here, and we go in the opposite direction for the same distance to correct its position. That's differential correction. Each observation is shifted back by the observed error at the base station. So the Trimble, one of the reasons why the Trimble, the yellow device that I showed you at the beginning, one of the reasons why it's so expensive is because it can automatically hook into this this system, the continuously operating reference station system, and calculate its corrective factor based on that system that's out there. Okay. There are two types of differential GPS, and I don't believe the book talks about it, but there are abbreviations. So there are a bunch of abbreviations. We already talked about PDOP and GPS, GNSS. It seems like in this lecture there's a lot of abbreviations, probably because it was invented by the government, but this post-process differential correction, in other words, the base station and the rover collect the information at the same time, but they're not talking to each other. So after the fact, they have to be recorded in their position. So after the fact, you take the rover position, you go back and you ask the base station, hey, what was the corrective factor after the fact with the files when you're done? That's post-processing. Sometimes that's referred to as PPRTK, or sorry, PPK, sorry, not PPRTK. Post-processing kinematic GPS. Post-process kinematic meaning that it's using the differential. That's sometimes referred to as PPK. Real-time differential correction has slightly lower accuracy. However, it's really the only way for it to work if you want to have the GPS using the corrective factor to navigate, because it broadcasts the correction in real time, so that when you're looking at your position, you're getting that precise centimeter to millimeter position in real time. This, you're not getting that because you're doing it after the fact. So this works great. It's less expensive. It works great for, like, if I want to go out and measure the position of a manhole cover. I can use that system because I just go out and collect them all. I go to the manhole cover, I sit on it, I collect it. I go to the next one, I sit on it, I collect it. Get them all done. Okay. This works better if you're. This is called RTK, real-time kinematic. This works better if you need to use the GPS to navigate, to get to a certain location. So inside of a drone, if it needed a precise location, this would be a better system, real-time kinematic. The accuracy is slightly lower, but you get a better location while you're in the field. It requires additional equipment, either a radio link, and sometimes now radio links are ideal because they work, wherever. But also you can use a cellular data card to get a link back to a satellite. So it requires a base station, and there's lots of base stations out there to use, but usually you have to pay to access the systems. Basically, you have to pay to process the software to get them to sync up. All right. So the wide area augmentation system, we'll talk about it here in a second, stands for WAS. It's like differential GPS, but it's an older system that only has a handful of wide area augmentation reference stations throughout the United States. So now instead of being at the most 70 miles away, we're talking about being at the most 500-600 miles away. However, what it does is it averages that corrective factor out between, like, let's say you're right here, it'll average out the error that it sees in all three of these, and it will be able to correct you somewhat. And we've, people have shown that it does work. Okay, it doesn't get you as precise as a true real-time or post-processed differential correction, because they're further away. The error is more unknown. Okay. But it broadcasts out through the system and it's a real-time system. So you can get if you go buy a GPS device and it says that it uses the WAS system, it's going to be better than just a system that uses the carrier phase and doesn't use the wide area augmentation system. So it's a differential correction technology, but the differential is not as precise because it's not as close to where you are. It's an old enough system that it's used a lot in airplane navigation. So most GPS devices that are loaded into airplanes use WAS, and it's precise enough to locate the position of an aircraft. Now, aircrafts have the advantage of being up above the clouds. Well, not the clouds so much, but being above they are above the clouds sometimes, but being above any other obstructions, buildings, or anything else. And if they're using the wide area augmentation system, their location can be down close to a meter, which is just fine if you're flying an airplane. Doesn't matter if you're 1 meter over from where you should be. You're still on the runway, or you're still on the path that you need to be. All right. So these continuously operating reference stations, I've already talked about and referenced them. These systems exist throughout the United States. You can see that there's lots of them. There are some areas where there's not as many of them, but there's not as many people living there. The University of Southern Mississippi, the Gulf Park Geospatial Center actually does a lot to maintain and update and to establish new continuously operating reference stations. So we should probably refer you to them if you want to learn more about that system. Okay. Now, another thing that the continuously operating system can do is, like the WAS system, you don't have to use just one ground station. So this is kind of like, in theory, you have your receiver, your base station. This is collecting a corrective factor that you're using to later correct it. Well, in practice, we can have multiple reference stations that each have their own corrective factor, and then figure out the average corrective factor for your exact location. So I can figure out the distance back to each of the reference stations and use that to weight the corrective factor and come up with a corrective factor at this location. And it's even more precise. We call that creating a virtual reference station. And most of these software packages that Trimble and the other Leica, the other guys that create these, that sell these products, a survey grade GPS product, will allow you to select multiple reference stations and create a virtual reference station in the software. So you can use them. So when you go to correct your location, you're actually not selecting a single base station, but multiple base stations. Your three closest continuously operating reference systems, or your 4 closest systems. All right, so here's the Minnesota. The book author is from Minnesota. All the virtual reference systems that could be created, and this is an example of a device that's doing real-time GPS corrections. He has this little device that's connecting in real time via radio link to the VRS network, the virtual reference station network. So you can get pretty accurate. This is where you get down to centimeter level accuracy using these type of devices that are using multiple nearby reference stations. The accuracy always declines in mountains, forests, or cities, and it will depend on the terrain and the PDOT precision. So here's the mean horizontal elevation and the position recorded, percent of possible. So any 4 satellites, okay, the PDOT is more than 4, you get a bunch more uncertainty. Okay, the PDOT is greater than 8. It's not quite as broad. Okay, most GPS devices and lots of the apps have the ability to show you where the satellites are in the sky relative to you, and they'll be moving. So this is one example of that. This is another example of that. And these each represent a satellite. And oftentimes, particularly in higher quality GPS devices, they can actually utilize both the global positioning system, U.S. government satellites, and the Russian system. So it's not uncommon, instead of seeing 8 or 9 different satellites at a time, to see, like here, this one's got 17 satellites. Okay, some of those are the Russian satellites and some of those are U.S. satellites. There's all sorts of application for GPS. I think I'm getting a little bit of a cough, but we got animal tracking. We talked about this on the first day of class. Navigation. That's something that you've probably all used, not on a device like this, but using your smartphone. Being able to, let's say, make a map of a field and show where the healthy plants are versus where the plants that need a little bit more fertilizer. Being able to navigate to that exact location and provide more fertilizer, that's something that's possible through GPS. You can use it to fly airplanes. Even lots of commercial jetliners use GPS to actually, assist the pilot in going where they're going. Not to mention the unmanned aerial vehicles that I talked about before. They use GPS to navigate to get to location. So commonly, when we make maps, like I use it in research to make maps of mangroves in the Caribbean. We don't actually take the drone and fly it, using the sticks and fly around the mangrove. I mean, we can, and we do that sometimes for informational purposes, but we want to actually make a map. We just plan a flight line, and the unmanned aerial system uses the GPS to actually navigate back and forth across the area to collect imagery over that entire area. I have a not very good example that I just, it's not such as bad. Well, here. Actually, I'll show one that's better. So this is from our last trip to the Dominican Republic. I wanted to create a larger area, that's why I was saying. Let's see if it. So these images have been stitched together. So this is a mangrove that are starting to grow shrimp inside the mangrove. Cut the mangrove down, grow shrimp. And so you can see these shrimp ponds that are coming through the mangrove areas. But this image was created. That's not what I meant to do. This image was created through all of these images that were collected. So these were all the original images. So you see how they're individual images. Okay. They're taking a few seconds to get sharp, but they're all images of that area, and they were stitched together to create that map. And the drone just went back and forth, and it was guided by the GPS system. So GPS is used in all sorts of different applications. That's what I'm trying to get at. Used to create all sorts of data. So this is an elevation data set that gets created from that other data. Field data collection. We use GPS all the time. If we want to go out and create a map, we go out and we can actually stand in the locations that we want to create and use the GPS to record a location. Whether that's, sometimes it's just using a smartphone type GPS or a Garmin type GPS, because the location, we don't need it down to within anything better than 1 to 5 meters. Or we can use a system like this, a survey grade or mapping grade GPS that'll get us down to either 1 meter. Mapping grade is usually considered about 1 meter. Survey grade usually considered, on the order of centimeters. So basically, it's like field. I used that concept before. It's like field digitization. Instead of you drawing it on your screen, you're standing in the field, physically digitizing a path or a point or some object. So it gets used a lot in that capacity. I mentioned earlier using a prism and a rod to get the location from a particular object. There are pieces of equipment that look like this, where you can. Well, we don't own one here, but you can utilize. You can look at something, put something in the crosshairs, and it will measure the angle of the device. Actually, it's using the same type of sensor that's already in your smartphone. It's just a little bit more precise. It can measure the angle, and then using a laser rangefinder, it can find the distance. So you can get an accurate location of some other position using a device like that, measuring offsets. In the end, it just produces an XYZ location at a point. You don't have to know all the math here, but basically it's just using trigonometry as a distance and an angle to find that point at the end of where this guy is pointing that device. All right, so this is the summary. Okay, you've got the 3 segments. The space-based positioning system with satellite. control, and user segments. So the carrier phase is the accurate one, the code phase, positioning, range measurements. The key to this is range measurements, distances. You've heard the term triangulate your position. This is actually trilaterating your position, or using 3 different distances to get to a position. So there can be different types of errors. Some of those errors are inherent in the system itself. And then some of those errors are affected by the environment, the buildings, the satellite geometry, and low PDOFs are better, and it's better not to be next to a building or next to a tree or under tree canopy. Averaging GPS locations almost always produces a more accurate position. There are many different correction approaches. We talked about real time. We talked about the WAS, and that's misspelled. It should be WAAS. And then we talked about post-processing. Both of these two would be based on using either the virtual reference system or just a single continuously operating reference station, or a base station that you set up yourself. So positional accuracies are always higher in sub-canopy or canopy areas. Higher meaning less accurate, I guess. The main application in GIS are for field digitizing, but also navigation and the other instances that I spoke about. All right. I'm losing my voice. But before, oh, go ahead. Anybody have any questions?
Real quick, when you say averaging of GPS points, does that mean like it's straight averaging, or is there a certain way you can do it?
Yep. So if I had my, I stuffed my smartphone in there. If I had my smartphone, I brought up an app that reported my position. Okay. I got my position. Here's the easting and the northing. Okay.
Right.
I say okay. And if I want to do that again, I have to maybe exit out of that, open up the app again, get another fix, do that again, do that several times. There are some GPSs that will actually end apps that allow you to continuously collect one. If I average those, and how do you average them? We're actually going to do that next week. But how would I average my position? What's the average? What's the average of 5 coordinates? How do I calculate the average coordinate based on 5 coordinates?
I'm assuming you add it up and then you divide it by the amount of time you're reading.
Yeah, so if I got 5 measurements, I'd add up all the x's and get a total of all the x's. I'd add up all the y values. So a coordinate is an x and a y. I add up all the y values and I get a total of all the y positions. Then I would divide each of those by 5, since I had 5 measurements, and that would give me my average position.
Okay, so there's nothing special when you're averaging coordinates. You're just straight averaging.
Right. Averaging. Now, if I were to calculate the center of a polygon, there are actually a few different ways or approaches to do that. With points, no difference.
Got it.
Like finding the geographic center of the United States or something like that.
Okay.
All right, but we're not doing that. We're just doing the points. Okay, so instead of taking a break, we'll just do this and then we'll be done for today, because this is pretty quick. And that way you can also ask me any questions that you have right now. All right, so it's going to be a 2-step process. Basically, you're going to go out and collect a bunch of points, and those are going to be the different points that were collected. So you're actually not going to collect 5 or 10 or 15 different points at the same location. Each of you is going to collect 1 measurement at each of these locations, only 1, and then together all of your measurements will be will be we'll average all of your locations. So next week, we'll average all the locations, and then we'll actually look at which locations were accurate, because I'm going to use the Trimble GPS to get the actual, well, we'll call it the high precision location of these objects, okay? And then we'll see how close we were. That's what we're going to do. And then we're going to answer a few questions. Let me make this a little bit bigger. View. Oops, no. There we go. Okay, so you're going to go out and do this. So unlike, this is still going to have 2 weeks to do the whole lab, but you only have 1 week to do this next part. And you should be able to complete this in a half hour. It will be uncomfortable because you have to go outside where it's hot. I don't know why it got hot. All right, so it's due 1 week. It's due before class so that I have time. I'll probably actually compile it during break next week. So I have time to compile it. So I'll compile them all together. Next week, you'll receive the remaining portion of the assignment as a class exercise, okay? So you're going to do the actual assignment next week. But I've already kind of explained what it's going to be. So this week, you're going to collect the GPS coordinates in the UTM coordinate system. So you need a device that can do that. I found a free app on both iOS and Android that will do this. There's one in Android called Handy GPS. I tried to get my phone, because I do have the ability to hook it up to HDMI, but I think it's going to HDMI and then it's going through VGA, so it's not showing up there. But you know, it's called Handy GPS. There's several of them, and it allows me to choose between UTM, latitude and longitude, and it gives me a coordinate. And it allows me to copy it to the clipboard. So I can copy it to the clipboard and paste it into another application if I don't want to write it down. However, you could just write it down. Okay? You don't have to use Handy GPS. There are a ton of paid apps that will do this. There's also a free iOS app called Locate that would work too. You're free to use any app as long as it collects UTM coordinates. So if it collects UTM coordinates, you're all set. So travel to the following spots on campus, record the GPS at that point. You don't need to set your GPS down. Don't set your smartphone on the ground and somebody accidentally drops it or steps on it and yells at me or something. You don't even have to take it out of your hand. I guess you could still drop it even if you didn't. But just go stand directly above it. And we're not worried about the elevation value, just the northern and easting, so it doesn't matter. As long as you're directly above it, hold it over there for at least 10 seconds, then record the value it reports. So you could just hold it over the location, and you don't even have to open the app for 10 seconds. What I'm saying is either open the app or reclose it and give me the value after you hold it there for 10 seconds. Because if you don't, it won't be quite as accurate. Okay, that's what I mean by some apps. This app, it actually doesn't report a new location until I refresh it. I have to. Actually, it is reporting a location, and it is reporting a location inside. Okay. All right. So yeah, just hold it over to 10 seconds, get that location, and then you'll be set. Okay. All right. So for the Hattiesburg campus, I've got 3 locations. So ask me right now if you don't know where this location is. So this one is the first location. You're going to get this corner of this drain. Okay, this drain, you can see the fountain. So this is that field that used to be, I don't know, it was the green building. I don't remember that, but there used to be a building on this field. So this is the Walker Science Building, the building that we're in. Okay, this is the quad with the X on it, and then there's another quad that's just all grass. Okay, so this is the first location. It's this drain, and you're going to get this north west corner of this drain. Close to that as you can get. Okay, if you have questions, ask. All right, this is the administration building. This says USM Army ROTC Alumni Walk. It's almost due west of the administration building. and it's got an N in alumni. The center of that N is the second location. And finally, we've actually got a USGS survey marker. This is a survey marker that's been measured and known to a very high degree. Okay, so this is a good one to get. This is the fountain. So you know the administration building is under construction. It's got yellow fence around it. If you go straight south of that, there's a little reflecting pool with fountain. I don't know if it's turned on or not. But then in front of that, there's this sundial, and there's a bunch of little seats around the sundial, and then you'll see this USGS marker is kind of almost beneath one of the seats, but it's not really beneath it. You can stand directly over it. Okay, it's not underneath the seat. It's peeking out a little bit from the seat. So that's the third location. 3 locations. Should be good. All right. Gulf Park people, I didn't travel down there yet. So again, ask me if you have questions. This is the FEC, the building that you're in, right here. Actually, I'll do it on here. This is the FEC, the building you're in. These are tennis courts. I believe this is now, isn't this now a basketball court?
Yes.
Yeah. So, but these are still tennis courts, right?
Yes.
Okay, so it's this corner. I called it the southeast corner of the southwest tennis court. It's that corner. Just get that little guy, the very outside edge, outside of the doubles line, not the singles line. The very outside edge of that tennis court, the corner. So that's location 1 for Gulf Park. Location 2. This is the what's the bayou called? Bear Point Bayou. So you go downstairs outside the walk over Bear Point Bayou, walk under the library awning, and if you keep going, just before you turn left, you could turn left this way. Just get that corner of that pavement. Okay. All right, and then the final one. This is the Friendship Oak. This is some of the leaves from the Friendship Oak. The flagpole is just off of this picture, and there's a little plaque out here, just a few feet from the flagpole, just west of the flagpole near this bench. So the center of that plaque is the final location for Gulf Park. So all you're going to do, whether you're at Gulf Park or Hattiesburg, then is put them in a table with the location, the easting, and the northing. The reason why I put them like this is the easting is the X, the northing is the Y. Sometimes the N will be reported first, like in some GPS apps, the northing is reported first, but make sure you put it in location, EN, and then location 1, the X coordinate, the Y coordinate, location 2, the X coordinate, the Y coordinate, location 3, the X coordinate, the Y coordinate. Okay? Except don't write X coordinate and Y coordinate. Write the actual numbers that you collect. So that's where I got. I was trying. Let's see if this works now. What's that? Oh. It's not reading my phone. Okay. So it's just going to have 3 lines in it. You could use, what did I say? Hey, I prefer to use Notepad or Excel, Microsoft Excel. So if you do this in Excel, you can save it as an Excel document. If you do it in Notepad, just, 1 on each line, 4 lines, that's it. All right? Anybody have any questions?
So I'm using this app, Locate, that you said about.
Yeah.
How do you get it to start?
I don't know. I don't actually have a device.
Just major reminders, and I don't get that extra Y. A bunch of different options. No, I didn't get that.
Maybe there's more than one app called Locate. Yeah. Oh yeah, this isn't the same app that I saw.
That handy GPS is on the Apple, Handy GPS? Yeah.
Oh, it is on iTunes? Okay.
Oh, is it the light? There's a green one. Yeah, the light.
Anyway. Okay, handy GPS. Okay. I'm having trouble finding that one that I found before. But I could try to find it. Yeah, this is the exact same one. Okay, this is the easting and the northing right here. Okay, so I'll update the lab to show that. Anybody else who has iOS? More people than Android. Okay, I got an Android.
Notes.
So latitudes, the northing and longitudes, the easting?
Yeah, well, neither one of them are latitude and longitude. It's a different coordinate system. So the UTM coordinate system has a origin, and it's expressing your distance in meters using the distance in meters north from the origin and the distance in meters east from the origin. So if you're right here, you could be 3 meters north and 2 meters east. Okay, so that's the east is the x. We call this the x, and the northing we call y. Okay. Now, latitude and longitude, you can put it on. It's not really meant to, but you can put it on x and a y. But latitude would be the y because it's going this way, and longitude would be the east because it's going this way. But typically, it's not a Cartesian system. It's for locating your position on a globe. And of course, we bring it up in GPS. It'll show up as an XY system. That's because it has to. It's a flat surface. All right. Any other questions? So don't send me the latitude and longitude. Send me the northing and the easting. Okay. And if you do have the option, this is the default. If you do have the option, make sure you choose WGS84 as your data. Yeah. It is the default, and it's really the only one there that we've talked about. So some devices will allow you to choose other datums like NAT83, which is very common. WGS84 is what we're going to use. So that's the datum. It's just the remember the datum is the approximate shape of the Earth that they used when they created the projection.
Are we free to collect?
Yeah, you guys are free to go. There's no sit down lab this time. All right, I'm going to end the call there. Alda.